Okay, now we move on to the next lecture, which will continue our understanding of the stratosphere and the troposphere. And I start with this simple model which we discussed earlier in this course, which is that the outgoing long wave radiation has two parts: the surface emission, which goes through the troposphere, and emission by the atmosphere. Okay. Now, if the temperature of the atmosphere is equal to that of the surface, you will find that OLR will not change. Okay. So, the greenhouse effect, which is the difference between the surface emission minus what is going out, minus OLR, will not change if atmosphere is at the same temperature as the surface. Okay. But we know that the troposphere is cooler than the surface, and so the greenhouse effect will be there. Okay. So, the key thing you have to understand is, because the temperature of the troposphere decreases the height, the greenhouse effect is positive. Okay. In the stratosphere, temperature grows up with height, greenhouse effect is negative. Okay. But right now, the positive greenhouse effect in the troposphere is dominating, so we have to worry about it. So, you must understand that the difference between troposphere and stratosphere, they behave differently because the lapse rate is different. Okay. So, the way the temperature changes in the tropostratosphere has a big impact. Okay. The emission from the top of the stratosphere is higher than at the bottom, because temperature goes up with height. Okay. On the other hand, emission from the top of the troposphere is lower than at the surface, because temperature decreases height. Okay. So, if you do a simple balance of energy in the stratosphere, it gains about 10 watts per meter squared, because ozone absorbs in the ultraviolet. Ozone also absorbs the emission from the troposphere, which is about 240 watts per meter squared, and it emits in both directions. Okay. So, you rewrite the equation, the temperature of the stratosphere is 120 plus 5 by epsilon. Okay. So, what this equation shows that as the epsilon increases due to increase in CO2, emissivity increases, stratosphere will cool. Okay. This is the phenomena which sometimes puzzles people, and you must understand that this is a consequence of the fact that in stratosphere the temperature is increasing with height because of the absorption of solar radiation in the ultraviolet by the ozone layer. Okay. So, I will talk about this further because this is very important. Now, this was shown more than 60 years ago by Nobel laureate Manabe when he ran a climate model and showed that as CO2 increases from 150 to 600 parts per million, the temperature in the stratosphere decreased and in the troposphere increased. Okay. Simultaneously, CO2 is causing a warming of the troposphere and a cooling of the stratosphere. Okay. So, this is a special effect of CO2 increase, and the other Nobel laureate Hasselmann called it a fingerprint. It's a fingerprint because the effect in the troposphere and stratosphere is exactly opposite. This will not happen if the incoming solar radiation increased for whatever reason. It will warm both the stratosphere and the troposphere. Okay. With CO2 it does not happen. So we can say with some confidence that the present cooling of the stratosphere and warming of the stratosphere shows that carbon dioxide increase is playing some role. Okay? If this was due to an increase in sunlight, then increase will occur both in the troposphere and stratosphere. Because it does not happen, we know that CO2 is playing a role in changing Earth's climate. So this fingerprint is very critical to identify what affect any gas on Earth's climate. Okay? So greenhouse gas affect Earth's climate one way, other gases affect another way, and this difference is visible in the observation of the troposphere and stratosphere, and so this fact has to be kept in mind. Okay? Now this is also seen in today's Arctic and Antarctic. Now Arctic has a very unusual feature that today in the Arctic, temperature does not decrease with height in the troposphere. In the first few kilometers in the Arctic and Antarctic, temperature goes up. This is called inversion. Okay? Now why does it happen? This happens because both Antarctic and Arctic have almost 6 months of no sunlight. So for those 6 months, there is continuous cooling of the surface of the Arctic and Antarctic during that winter due to cooling by emission to space. So even after summer comes in, that inversion still is there, it doesn't go away. Okay? And so when the CO2 goes up in the Arctic, in this region of the Arctic near the surface, there is a negative greenhouse effect, okay, which you will not see in the tropics. The tropics, as the global warming occurs, temperatures increases in the surface, but it increases more at upper levels. While in the Arctic, it's very different because of the inversion. Okay? So we already see that any change in the temperature gradient in the troposphere and stratosphere has an impact on the greenhouse effect. Okay? So in the Arctic region, there is a negative greenhouse effect because there is a inversion, which is not there in the tropics, for example. So please keep this in mind. Make sure you understand greenhouse effect correctly. It need not always increase temperature. It increases temperature in the troposphere because temperature goes down with height, but in the stratosphere it goes up. In the Arctic, in a small region near the surface where temperature goes up, again there is a negative greenhouse effect. Okay, let's go back and look at the radiation budget of the Earth once more to understand some of the results. So the key point about the Earth radiation budget is, of the 341 watts per meter squared of sun's radiation that comes into the Earth's surface, about 160 reaches is absorbed at the surface. About 23 watts is reflected by the land and ocean. About 79 watts is reflected by the clouds and the atmosphere. So about 1/3 or about 30% of the incoming radiation is reflected back. This is the albedo, around 0.3. Okay? Now let's go to the thermal infrared, where the Earth emits radiation about 396 watts per meter squared. Notice that about 333 watts is returned back to the Earth by the greenhouse gases. Okay? So greenhouse gases are returning most of the radiation by the Earth back, okay, and of course it also these gases emit radiation to space. That's around 239 watts per meter squared. But notice that of the 396 watts meter squared emitted by the Earth's surface, only 22 watts escapes in the region 10 to 12 micron, the so-called window escapes. So 95% of the emission of the Earth's surface is returned back to the surface. Only a small portion reaches space. Okay. So this is the role played by greenhouse gases like CO2 and water vapor. Now, if you recall the simple energy budget model that we talked about earlier to understand the global mean temperature, in that model we assume that the radiation emitted by the troposphere downwards and upwards were equal. It was assumed that the Earth's atmosphere, which is mainly the troposphere, emitted equal. Now we want to modify that. In the light of the radiation budget just we saw, we want to make sure that epsilon downward, emission downward should be more than emission upwards because of the decreasing temperature with height. So in the original model we ignored it for simplicity, but now I want to include it and see the effect. So I want to, based on observation, I want to make epsilon downwards larger than epsilon upward. We will assume epsilon downward is 0.95 and epsilon upward is 0.54, which reflects the fact that troposphere is not isothermal. Okay. We also want to include the evaporation and turbulent fluxes, which we ignored in the initial simple model. In the Lewis model, this was ignored. Okay. So we add that. So there are two changes. One, that the emission is not equal up and down, which was not a good assumption, and neglect of non-radiative heat transfer between surface and the atmosphere, which is also important. It's around 100 watts per meter squared. We cannot ignore it. So if you include these two, the equation changes. So you can see at the top of the atmosphere, radiation absorbed from the sun is equal to what is emitted upwards of the atmosphere and what is transmitted from the surface. Okay. Now at the surface, the radiation absorbed from the sun after reflection and absorption by the atmosphere, then the downward radiation from the atmosphere, which is absorbed by the Earth, which is a black body, radiation transferred from the Earth to the atmosphere by evaporation turbulent fluxes, ETF, and the radiation emitted. This is the energy balance for the atmosphere, which absorbs the radiation emitted by the surface and also the radiation emitted by the atmosphere upwards. Okay. Now, if you take the ratio of these two equations, I have written it in the equations here again. This is the balance for the stratosphere, balance of the surface, and balance at the troposphere. Let me go back. So this is the equation which we are solving, and this ratio of these two equations is here, okay, and we get the ratio B to C as the surface temperature. Okay, I am assuming upward emissivity is 0.9, downward is 0.54, albedo is 0.3, incoming radiation 1360, solar absorbed 0.2, and evaporate turbulent flux is 110. Okay, if you do all this, you will get the answer of close to 288. So what I have done really is I have slightly modified the Lewis model to include the fact that radiation up and down by the troposphere is not equal, and included the non-radiative process, but still able to get 288. Okay? So this is a model which is superior to this model, which was obtained from textbook of Liu. Okay. So what I'm trying to point out that the simple model was useful, but not totally right. We can make small changes, still get almost the same answer. Okay. Now I want to further modify the model to include the stratosphere. Okay. Stratosphere is important because it has the ozone layer. Okay. In the this model also, we treated the entire troposphere stratosphere as a single layer, which is not correct. Okay. Because the temperature variation is not the same. Okay. So now you do a two-layer model. We treat the troposphere at one temperature T1, and we take the stratosphere to another temperature T2. Okay. We do an energy balance at the stratosphere, at the troposphere, and at the top of the atmosphere. Okay. So all these are here for you to look at. Surface is here, troposphere is here, and stratosphere is here. Okay. And if you add all the three, you will get the top of the atmosphere. Okay. Now you will see that for simplicity, I have assumed the emissivity of the troposphere to 1. Last time it was 0.95. Here I assumed 1 to make the equations easier. But the emissivity of the stratosphere cannot be 1 because it contains very little atmosphere, very little water vapor, some CO2, some ozone. So the emissivity of the stratosphere will not be much higher than 0.1. Okay, because the amount of mass of the stratosphere is very small. Okay. So if you take all the account and you solve this equation, you get the following equation for stratospheric temperature, which depends on the solar absorptivity of the stratosphere, which is due to the ozone layer. Okay. And also the emissivity of the stratosphere. And this is a general equation now. Now you look at two limiting cases. If you neglect the solar absorption of the stratosphere, then you get a simple equation for temperature. And now if you consider increasing CO2, that is emissivity increasing, you will find temperature will decrease. So the key point is, if we neglect the absorption of solar radiation by the stratosphere, then the greenhouse effect in the stratosphere will be positive, like in the troposphere. So the greenhouse effect is negative only when you include the absorption of the solar radiation, which is shown here in part 2 here. In 2 I say A2 is not 0, okay, but epsilon 2 is very small because it's close to 0.1. Then you look at this equation, then you see that if you now increase emissivity, this decreases and this increases, so T2 will increase. Okay. Sorry, let me go. If you increase epsilon 2, this term will reduce, so T2 will decrease. So if you make A2 0, no absorption in the stratosphere will warm due to greenhouse effect. The same stratosphere include the ozone absorption by solar radiation, it will cool. So this is a very important thing which I brought out through a simple energy balance model. Please examine it carefully with what we did earlier, and so you can understand the greenhouse effect being negative in the stratosphere either through this energy balance model, or if you don't understand it too well, you can take the other view that because the temperature in the stratosphere is increasing, because of this CO2 emits more radiation here than here, and hence CO2 increase will cause cooling is also equally valid understanding, but that is more what you call not quantitative but qualitative. Qualitative is okay, But you want a quantitative understanding, then you have to look at this equation which I have developed here, and you have to understand how the energy balance in the stratosphere and troposphere is different, and that makes the role of CO2 very different. The role of CO2 here is to change emissivity here, but this effect is through this layer, and so increasing CO2 causes warming. But if you assume that A2 is 0, if A2 is not 0, then this term becomes very important. If A2 is 0, the term drops out. Okay, so you get a very simple equation. If A2 is not 0, this term gets complicated. You have to address this equation. So I would argue that understanding the stratospheric warming and cooling due to increasing greenhouse gases is best done through energy balance. Okay, so I want you to look at this carefully, make sure you understand what this does. Okay. Now, so far you only talked about one layer or two layer, but atmosphere is very thick, has many layers. Okay, so you can extend the analysis we did with Lewis model to n layers. Okay, and these n layers will have balances at various levels. Okay, and to make the analysis simple, I will assume that these n layers are transparent to solar radiation. Okay, it's not correct, but for simplicity we will do that, and we will assume that the n layers which are absorbing the emission by the Earth's surface like a black body. So there are two approximations: one, neglect of the radiation from solar by the layers, but total absorption by the of the Earth's radiation. So this analysis then becomes simpler, and I will continue this discussion in the next lecture and show how this shows that if you have a large number of layers which absorb Earth radiation totally, then the greenhouse effect increases rapidly. Okay, so that point I want to make before we go on to further discuss the greenhouse effect. Thank you.